All right, folks, let's finish up our notes here. Looking some more at limits. So evaluate for each of the following functions. You don't need a calculator. Don't use a calculator if you don't have to. And PSS, you shouldn't have to use a calculator. So we're looking at the limit of the natural log function. Now, sometimes you can plug in, sometimes you can plug and chug. Other times, it's better to just try to make a quick sketch and use that sketch to help you figure out the function values and the limits and things like that. So this is an easy one to sketch, natural log, no shifts, no stretch shrinks or reflections, so life is good. There's my graph of natural log. So what's h of 0? Well, if I plug 0 into this, we're trying to natural log a 0. That's bad news. You can only log any kind of log positive numbers. So this would be a DNE. What's the limit from the left? Well, as I approach 0 from the left, there's not even a function over here. So there's nothing to even try to evaluate. That's definitely does not exist. Coming from the right. Now, as I approach 0 from the right side, where's my graph headed? Down, 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 down. So that would be negative infinity. And then remember, the overall limit is what's happening from the left and from the right. Are the two roads at the same height? No. One doesn't exist and the other one's down at negative infinity. So that would be a does not exist. All right, I'll give you a little bit of a head start. I'd like you to try to sketch 1 minus x. Sorry, 1 over x minus 3. That was not very descriptive. Sketch 1 over x minus 3. If you haven't paused yet, pause. All right, let's see how you did. So this is a rational function, a reciprocal function with a shift of +3 horizontally. So I'm just going to estimate. I know where that is. I don't need to put any tick marks there. So the rationals are positives, so everything's where the positives would be positives and the negatives would be negative. All right, let's plug in. So f of 3 does not exist. There's no point there. We have an asymptote. When you plug in 3, you get something that's not 0 on the top and you get a 0 on the bottom. What's the limit as we approach 3 from the left? This goes down to negative infinity. What's the limit as we approach 3 from the right? That goes up to positive infinity. My overall limit is what's happening to my one-sided limits. Are they at the same height? While they're both infinities, they're not the same kind of infinity, so we would call that a DNE. I'll give you actually just pause, take as long as you need. Make a sketch of 1 over the quantity x plus 2 squared. All right, let's see how you did. So this is a reciprocal squared family with a shift horizontally of -2. So it's going to take me back here. It's going to keep that asymptote there. We've got positives, so there's no reflections, there's no stretches, so this is what my graph's going to look like. All right, so what is happening to my function at -2? There's an asymptote, so that point does not exist. There is no function value. What's my limit of -2 as I come from the left side? This goes up towards positive infinity. What's my limit as I approach -2 from the right side? That goes up to positive infinity. And so if the two limits are the same, I don't like this, but everywhere I look, it seems that it's legal. The overall limit then would be positive infinity. All right, now this one's going to take some doing. So I'm going to review with you how to sketch secant of x. Let's go ahead and get a little grid going here. When you do trig, usually you just want to go forward. I'm going to put in 4 tick marks, and I'm going to encourage you to graph. Okay, who is secant related to? Secant and cosine are buddies. So we're going to think about secant as cosine. So I'd like you to graph just the points, don't actually connect the dots. What are the points of cosine? If you haven't paused yet, hit pause. Okay, cosine. So what I would do is I'd think about the unit circle. I'd start here. What is the x value here? That's an x value of 1. What is the x value here? 0. The x value here is negative 1. The x value here is 0. The x value here is positive 1. So that's the graph of cosine. We would connect it with a smooth curve, but we want to reciprocal all those values. So what's the reciprocal of 1 is 1. What's the reciprocal of 0? Undefined. What's the reciprocal of negative 1? Negative 1. What's the reciprocal of 0? Undefined. What's the reciprocal of 1? Is 1. And then remember, from here, we take the graph and actually kind of turn it inside out. We spin it around, and so this would be the graph. So if you didn't remember that, that's no biggie. I don't mind right now. I mean, now we've seen it again, so I would hope that you could remember it from here. Let's look at this now from the perspective of pi over 2. So which one of these tick marks is pi over 2? Well, remember, if you go one full lap around the unit circle, you have gone a distance of 2 pi. So if this is 2 pi, then that would be halfway there would be pi, halfway there would be pi over 2. So this is where pi over 2 is. So what's our function value? Well, it's an asymptote, and there is no point on the asymptote, so we have a point function value that does not exist. As we approach pi over 2 from the left, from this side, my graph is going up towards positive infinity. As we approach 2 from the right, my graph is going down towards negative infinity. And if my two limits are headed in opposite directions, then our limit would not exist. Done. What do you think? All right. So let's see. Here's our function. Is continuous for all x that are not equal to negative 1/2. All right, that might come into play later. I'm not really sure why we have that there yet, but we'll see what happens. So let's figure out what's the limit as we approach x equals negative 1 from the right side. Well, let's try to direct substitute first. If we can direct substitute, game over, and that'll be our limit. So I would do negative 1/2 Actually, you know what? I'm going to try to see if something cancels first, because I don't want to try to square negative 1/2. So let's go back here to the function and see if we can mess around. So I know that factors. That factors into x plus 3x minus. Pause. You should do this on your own. Factor that denominator. Pause this and try to factor the denominator on your own. All right, so let's see. 2, I need a 2 and an x. I need to make a negative 4. And then, so this would be a positive 1 to add up to negative 3. So now I see a couple of things. I notice that we've got a hole. We've got a hole at x equals 2. What else do you notice? You should notice 2 more things. I know we have a VA at x equals negative 1/2. Now I see why they're talking about negative 1/2. And one more thing. We have a 0 at x equals negative 3. And you might look at that and you say, gosh, how am I supposed to remember all these things? Just think about it logically. I mean, think about what happens if you put negative 3 into this. You're going to get 0 over, I'll do this in a different color so you don't get confused. If you put if you put negative 3 into this, you're going to get, I can't come up with a good color that I want to use. I'll use this blue. Put negative 3 into this. You'll get 0 over something that is not 0. What is something divided by something that is not 0? It's a 0. What happens when I put negative 1/2? I put negative 1/2 in this, I'll get something that's not 0 divided by, put negative 1/2 in this, I'd get a 0. So where's the 0? It's on the bottom, which is the worst thing that can happen, which creates the worst thing that can happen to a graph. And then when I put 2 in the top and I put 2 in the bottom, here I'm going to get a 0 on the top, I'm going to get a 0 on the bottom. So I know there's going to be a hole Now you might say, well, wait, didn't we cross those out? Yeah, you don't want to cross them out. I mean, you do cross them out, but you want to still remember that there was a hole there. You know, it doesn't eliminate the hole. It helps us figure out how to graph this thing, and then we have to remember that there's a hole still to think of. So once I've got the hole kind of taken care of, I don't have to plug in. The only time I have to worry about the hole is when I plug in what number? 2. If you plug in anything else, whatever you put in here will be the same thing that you put in here, which means these two things will always cancel out and not cause an issue unless that x is a 2. So what I'm going to do now is I'm going to take this negative 1/2 and I'm going to plug it in for the x's of what's left over. So I would get negative 1/2 plus 3 over 2 times negative 1/2 plus 1. I don't know why I put parentheses around that. So this would equal, what would that be? 6 over 2 with a negative 1 would be 5 over 2. Over 2 times negative 1/2 is negative 1. Negative 1 plus 1 is 0. This means that I have a VA here. So if I have a VA, what's my limit? My limit. Oh, wait. We can now figure out. This is harder than I wanted it to be. I wanted it to just be D and E. I mean, to figure this out, we'd have to do a quick sketch. Let's see if we could do a fairly quick sketch. Oh boy. Okay, this is what our function is going to look like except for the hole. So we have an HA of 1/2. Y equals 1/2. We compare those. We have a VA of x equals negative 1/2. I have a 0 at negative 3. We have a y-intercept at positive 3. So we can get a fairly quick sketch going here. And what would we get as we approach? What would we get for our limit as we approach negative 1/2 from the right side? We would get positive infinity. What would happen as we approach? Okay, so look, 1 is a dream. 1's great because 1 isn't any of our weird things that are happening. So you can just plug and chug 1, and whatever the answer is, that's your answer. So this would be equal to 1 plus 3 over 2 times 1 plus 1. 1 plus 3 is 4. 2 times 1 is 2 plus 1 is 3. So we would get 4/3. Game over. I love those. Because our function is continuous there, we're not going to run into any problems. What is the value of k? So in other words, what they're asking here is what height is the hole? If you can figure out the height of the hole, then you'll know what you would need to do to plug in for k to fill in so that our function is continuous. So what I'm going to do is I'm going to go back to my function. I'm going to eliminate the hole, and I'm going to plug in x equals 2, because whatever I get then, that should be the height of the hole. So my hole will be at a height of 2 comma 2 plus, that's 5 over 5. Yeah. I'll do this over, I kind of don't like what I did there. So I would go 2 plus 3 over 2 times 2 plus 1. So that would be 5 over 5. So that would be 1. So my hole is at a height of 2 comma 1. So then what should k be? What y value should we have at 2 so that our function will meet up? We should have k be equal to 1. We want it to be that y value right there. All right, last kind of discontinuity, and this is another one that you don't see very often, and I'm just going to do it all on my calculator. So what's the graph of sine of 1 over x? I would not expect you to know how to graph this perfectly. I was surprised that this graph even existed. Okay, so this is what we call a monstrous function. So sine of 1 over x, I'm going to go back to my mode. Anytime I try to graph, I want to be in radians. Anytime I want to do like inverse, sine inverse of something, I want to be in degrees for that. But for graphing, I want to be in radians. So I'm in radians. I've got my equation. I'm going to do a zoom 6 to give me a standard window. And I can see that it's way too big. So I'm going to look at I'm going to shorten everything up, especially my y values. So let's say we go from -3 to 3, and let's say we go from -2 to 2. Look at this crazy graph. It comes in, everything's normal, everything's hunky-dory, and then all of a sudden, it just goes absolutely bonkers. So I'm going to actually zoom in a little bit more, go from -1 to 1, and go from -1 to 1. Look at this thing. Here it comes. And all of a sudden, it gets to this spot, and then this should actually be full of, it should be like solid full of a bunch of different points. So if I were to sketch this thing, it bounces between 1 and -1. And it comes in here like this, nice and smooth. And then it gets to this spot. It shouldn't go down like this. It should go like that. And then it just goes crazy in here. Blur, and then it comes out the other side all nice and smooth again. So that's actually asymptotic. That's a terrible graph, but asymptotic to those places. This is what we call an oscillating discontinuity. The function oscillates between 1 and -1 over and over and over again. So, I mean, there isn't much to say about it. The limit of our function, could you predict what it's supposed to be? I know it's going to be somewhere between -1 and 1, but I couldn't tell you the exact value. So as x approaches 0, we don't have an answer. That one, like I said, is not super important, but I'm glad we got a chance to at least talk about it so we can refer to it if we ever see it again. So what's the idea now of finding the limit versus finding the function value? So when looking for a limit, this is a picture of how you look for a limit. So in other words, you can pretend like you don't have any idea. You have this thick vertical line covering up the point. You don't know what's happening to the point, but what you're looking for is what's happening to the graph. Coming from either side, what happens? My graph meets. So my graph meets from either side. Therefore, my limit exists. They head to the same place. Now, when you're looking for a function value, when I'm trying to figure out the function value, I don't care what's happening from one side to the other. I don't care where the graph actually goes. What I care about is where the point is. And the way he drew it here, he had the function meeting up here when the actual point, the function value was down here. So the function value doesn't care where the graph is supposed to go. It's just wherever the graph actually goes. So let's do let's look at a bunch of different. So this is what that picture was supposed to be. So if you unveiled this, so what he did here was we didn't know what was happening at the point, but we knew that the graph met. That meant that the limit exists. We didn't know what the graph met or not, but we knew that the point existed. And in this case, this is what I call a holy jump. Nobody else, if you ever, besides kids who have had my class, would know what a holy jump is. But that's what I call a holy jump, because it's got a hole that jumps out to a point and then jumps right back into the hole. Okay, so let's do some limits now. So based on the picture, now you've got to pay attention. A couple things you're looking for. You're looking at, is this an overall limit or is this a one-sided limit? Overall limits are coming in from both sides at the same time. One-sided limits are just looking at it from one perspective. So as x approaches -2, so here's my picture, here's -2. As x approaches -2, this side goes to infinity, this side goes to infinity, positive infinity, positive infinity. So my overall limit, positive infinity. What's happening as we approach 2 from the left side? So here's 2. As I approach from the left side, I'm going to a height of 5. That's my limit. The y value, the graph is trying to reach a height of 5. Does it actually get there? No, but I don't care. A limit is what the graph intended to do. F of 4. Now this is saying what's actually happening when x is 4. So I would go to where x is 4. I would trace up wherever the graph is or whatever the graph is doing at 4. That's going to be my answer. So the graph is at a height of 5 when x equals 4. It doesn't matter that the two branches met. It only matters that they're attacking. They're actually, I shouldn't say not attempting, they're actually at that height. What's happening to the limit as x approaches 4? So I'm following this in. I'm following this in. Are both one-sided limits headed to the same place? Yes. Where is that place? 5. So the overall limit would be 5. What's the limit as you head towards 11 from the right? So I got to go past 11 and come in from the right. So coming in from this side, I would reach, this is also a height of 5. Does it actually get there? No, it does not. It's an open circle, so there's a hole there. We don't actually get there, but that's not what a limit is. The limit is what the graph intended to do. What's the limit as we approach 5 from the left? So here's 5. I'm coming at it from the left side. So as I approach from the left side, my graph goes up, 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 up to positive infinity. Why don't you pause and try to do the second half? And then unpause every time, after you try one, unpause and see if you did it. Okay, f of 2. This is asking me what is the function value at 2. So I go over to 2, and lots of stuff is happening at 2. But only one of them is the actual point. Only one of them is the actual function value. This is the one-sided limit. This is the one-sided limit, and that's the function value. So my function value is 4. Pause again. Try the next one. Okay, what's happening as we approach 6 from the right? So here's 6. I'm coming from the right side. So from the right, I'm trying to get to a height of 3. I don't actually get there, but it's where I'm trying to go. I'm not going to keep reminding you. Pause on your own. What's happening as I'm approaching 6 from the left side? So as I come to 6 from this side, I only reach a height of 2. It doesn't look like it's going to be in here. What would be the overall limit then at 6? The overall limit would be D and E because they approach 2 different heights. Okay, this is not a one-sided. This is just saying what's happening as we approach 8 from either side. So as I approach 8 from this side, I'm at a height of 3. As I approach 8 from this side, I'm at a height of 3. Where's the actual point? It's up here at 5, but that's not what the question is. The question is, what did the graph mean to do? What did it intend to do? It intended to meet at a height of 3. What did my graph intend to do? No, sorry. This isn't intending. This is what's actually happening at -2. So I track over to -2. Now, if you look quickly, you think it's just an asymptote. But he made it a weird function that has a point. And you might say, well, wait, can you do that? You can only do it with a piecewise graph. But there is a dot there, which means there is a function value, and that function value is a height of 2. And then last, I want to approach 0, and I want to approach 0 from the left side. So here's 0. I'm going to come at it from the left, and my graph is trying to get to a height of 2. Okay, so that's a lot of notes. That's a lot of notes, okay? A lot of information, but this is the foundation. Limits are the foundation for the rest of the course. I mean, we use limits for the rest of the way. So good luck on the homework. Go get them.